Let me start. Okay. Okay, hello, this is Group 2's presenter Kyonan. Let me start our final presentation about a self-powered underwater data center. These are today's contents. First, I'm going to show the current data consumption of our data center and the cooling problems. Then, the introduction of the project Netic done by Microsoft, one of the successful underwater data center will be presented. And finally, we're gonna introduce our self-powered underwater data center. First, let's start with the power consumption of current data centers. From this figure, you can find that almost half of the electricity is used for the data center cooling and the power provision systems. But the cooling system is necessary for ensure a server lifetime, and it makes the server center, data center more efficient, and the lifespan of the server becomes longer with the cooling system. So we can say that the cooling system is quite necessary for current data center. However, the data center cooling is expensive system. As you know, the cooling system needs an additional power, and the coolant such as water are needed to construct the data center cooling. For this point, being underwater can be simple and effective solutions to construct the cooling system. The left image is the sample image of the underwater data set servers done by China. Using underwater data servers, the power usage effectiveness, the PUE value can be much smaller than the current data centers. For example, the NATIC project made the PUE value as 1.07 value, and the average values are near to the 1.2. So let me introduce about the case study of the Microsoft project NATIC. The key idea of the NATIC project is using an underwater pressure vessel to contain the data servers. The server racks are contained enclosed with the cylindrical pressure vessel, which can hold the system underwater. The vessel size is 12.2 meter length, and this diameter is about 2.8 meters. And with some additional devices, the diameter becomes the 3.18 meter. This size is quite similar with the conventional container box, like this image. The 12 exact name is about the 20-foot equivalent to the container box. So each pressure vessel can contain 12 racks of the service, and these racks include 864 standard servers inside. And the total storage of the service are about 27.6 petabytes of disk. And the power consumption of this service about 240 kilowatts per each vessel. And the vessels are filled with the dry nitrogen of the 1 atm pressure. Finally, the vessels are placed underwater in 117 feet deep water. This is about the 35.66 meter under the surface. So with this, the project NATIC, the result of the project NATIC was quite successful. The underwater data servers were well operated for the 2 years, from 2018 to 2020. And from the research, the actual customer benefits of the customer can be summarized like this. First, project NATIC can ensure a rapid provision. The system do not need additional server containing buildings, so the deployment of the service can be fast and it would be no more than 90 days. And this system enables rapid response to market demand. And secondly, because the servers are placed too near the customers, the response time for the server becomes much more faster than the conventional data centers. Lastly, the pressure vessel systems show much lower server failure rate, which means the better reliability. And the actual failure rate were about 1/8 from the land-based data centers. This is because of the special environmental condition, the stable outside temperature and the nitrogen gas infill. And finally, the vessels can be recycled and reused after the recollecting the data service. From using these backgrounds, we want to suggest a self-powered underwater system. The key features of the self-powered underwater data center is two. The first is the underwater server using the pressure vessels, and the second one is power generation plant. The underwater server will be enclosed by a cylindrical pressure vessel. This shape is the strongest shape to contain the server racks against the water compression. The safety of these types of structure is proved by the project mapping. The one design consideration is the vessel must have as few joints as possible. The joints are the main causes of the leakage, and also it became a weak point of the structure failure. The underwater vessel system will be installed in the middle of the tidal lagoon, which I'm going to explain later. The second part is the power generation plant. The main structure of the power generation center is the tidal lagoon. The tidal lagoon generates electricity with the tidal energy using the kind of tidal volts. Wrapping this area with tidal barrage and the seawater turbines, it can generate tons of electricity. And the lagoon can be a kind of barricade to uh, protect the server vessels from the external threats, such as the pirates or sharks or the extreme waves itself. And also, we would like to install another offshore wind turbines to generate more electricity. These turbines will generate electricity via the coastal wind flows. And for the data transmission, we're going to use the wire connection. Using the fiber optics cable, we can connect servers to internet with enough speed and stability. The specification of the fiber optics cables are like this table. This cable can ensure the much faster data transmission speed. It's about 9.5 terabits per second. This is about the 125 gigabytes per second. And the conventional data center speed are about 10 to 100 gigabytes per second. And this cost is like this. And following this table, you can imagine that the table are quite thick and stable. And the risk of damage would be like this. But because our system is surrounded with the tidal lagoon, so most of the damage resources can be separated with our cables. We can prevent this kind of problems from our system. And the cables are quite reliable, so we can expect the stable and fast connection with the outside internet. So the major advantages of the self-powered underwater systems are like this. First, it can make efficient cooling of the data center. The cold seawater can be great sources of the cooling system, and it can increases the cooling efficiency rather than the land-based data centers. And from the results of the project Matic, the pressure vessels can make reliability and sustainability more better than land-based data centers. Because of the nitrogen filling and the stable temperature condition, the device can operate with some very stable situation. And as you know, the systems are placed underwater. It can be a better security condition. To make a secure condition, the land-based data centers mostly use some additional security systems such as human guards or something. But because this system is placed underwater, the deep underwater can be a big obstacles for the external intrusion, and the tides and the lagoon works can be additional barricades. Lastly, because the systems are physically close to the server customers, it can ensure the physically faster connection with the server users. Compare with the actual land-based data center, we assume that the server unit and the server system is same equivalent with the tidal lagoon of the Swansea. So this is the Swansea tidal lagoon, and or the first tidal lagoon power plant, has the 11.5 square kilometer area, and its annual output is about 400 gigawatt hour. And in this slide, we just compare the actual operational cost of the land-based data center and our system. To make a simple comparison, we found some data of the actual land-based data center. From the Amazon Web Service, its servers are about to 50,000 and 80,000. So we assume that the typical one is about the typical data centers have 50,000 servers, and it spends 196 terawatt hour per annually. So to become an equivalent condition, we assume that we have 60 vessels of the project Natic. So we have total 551,000 and 840 servers inside the pressure vessel. And we assume that the tidal lagoon is the same one as the Swansea. And we installed about the 2.5 megawatt sized wind turbines in the offshore. And in this area, 11.5 square kilometer can install roughly 81 wind turbines. And we assume the 25% capacity factor. With some simple calculations, the net consumption of each center are like this. So the typical land-based data center uses the 160 to 96 to 400 terawatt, and plus alpha means about some additional operational power consumption. And our system uses about 126 terawatt hour, and it generates the electricity. So the power generation are subtracted from the consumption, and plus alpha is also equivalent to about the operational power consumption. So finally, we compared the power consumption and some other features of the land-based data center and our self-powered underwater data center. For the power consumption, we calculated that the land-based one is about to use the 196 terawatt hour, but our system with some power generation spends 125 terawatt hour. And from this point, nearly 36.2% of the power consumption can be reduced with the underwater system. And for the installation space, the actual land-based data centers need the massive area of the land, but the pressure vessels can be placed underwater, so the efficiency of the space utilization is much better than typical one. Finally, the eco-friendly one. To build additional buildings to contain the service, it has much materials and is kind of not recyclable, but our pressure vessel tanks can be recollected and recycled or even be reused after the usage. So we did our job like this. I did about the power generation methods and take presenter as the final presentation. And Muhammad did about the communication methods from the table, and he did the proposal presentation. And finally, like I say, researched the safety methods and did the midterm presentation. These are our schedule and timeline. Until the week 5, we gathered some of our ideas and allocated the jobs into 3 parts: communication, power generation, and safety design. And until the midterm presentation, we just suggested our possible solutions of the system and did the midterm presentation. And finally, today we have suggested quite detailed solutions for our system for the communication and power generation and safety design. And this is for the end of our presentation. Thank you.
From other team? I have well, have you ever consider about the maintenance of surface? For example, monoclothes or seaweeds can attach to surface of system.
Yep.
I think that kind of things uh, make lower heat transfer. So I think that kind of things make hard to get out. So if you ever think about like that.
Yeah, I understand what you want to say, but actually the heat transfer is not proceeded with the actual the tank surface because there is additional heat transfer devices inside the tank, so you don't have to worry about the surface effects.
Thank you.
No. Okay. Can I know the specific area that you want to build the center and just look at the, the location?
Actually, as you know, the tidal berries or the kiloton are very limited, have some limited spots. So our idea is if we about adding some data centers of the current lagoon structures. So maybe this one G tidal lagoon can be a one candidate.
Is that the only reason for
Pardon, can you say?
is that is that reason is the only the reason for the tidal energy, or is there any extra reason? Wondering.
I think surely the main purpose of the system is make efficient cooling with the water. So actually, it doesn't have to be the sea. Maybe we can install the system as the river or something. So, but the tidal energy is quite great energy sources, so we can produce another power generation with this.
And one more thing, when somebody asks about that questions, that you told about the surface is not really affected by the cooling, but that way, why don't we just build a data center near the cool water onshore?
Yeah, actually there was a patent about that system. The system uses the water pumps to pull off the cold water from the sea and use the water as a coolant and get back to the sea. But as you know, the pulling up the massive amount of the seawater is by over usage of the power. So being underwater is quite more efficient way to make the system more cooling.
Uh, uh, the NATIC project has shown the submergence depth. How deep is the system?
The 170 feet.
Oh, have you tried to the comparison table with the land-based dam? The big one is good, but my question is, have you tried to show us cost estimation of comparison?
Actually, yeah, I tried to find the actual cost of the underwater system, but as you know, the underwater power data centers are just beginning of the system, so there is no much open data. So, and but as you know, as we wrote this the second part, building on land is some additional the land fee kind of, and the building costs, and the system underwater is actually do not have much of them. So maybe we have some get some trade-off of like the founding costs. So we just try to compare the operational cost.
Uh, when you do a new project as an engineer, most of the time you cannot find the existing ones or cost. Then what you should do, you can estimate by using a component of their system. Component-wise cost adding up. That is the usual way. Otherwise, you cannot start your project because the managers want to see whether your new system is economical. Every engineer needs to do for the new project. Right. That is the one tip. And then another question. What can be the disadvantage of this normalized data set?
That would be, as Sungyu said, the additional effects of the sea biomatics or something. The maintenance could be harder than the onshore data centers.
There can be more disadvantages. So you need to also show us the list of possible disadvantages or the more reasonable comparison and selection. All right, thank you very much.
Thank you.